Hello everybody, good evening. Thanks for joining. My name is Henrik Plate. I'm from Endor Labs, and I will talk about attacks on open source supply chains. So we all use open source, a bunch of open source, but unfortunately a couple of years back, attackers kind of discovered this as a viable means to inject malicious code into your supply chains. And what I will talk about in the next 45 minutes is I will provide you a lot of examples on actual attacks or vulnerabilities that could have led to an attack, or just proof of concepts showing you all the different attack vectors. I will then provide a more systemized or systematic overview about those attack vectors. And then at the very end, I will briefly touch upon a couple of safeguards. Here again, the QR code for the lightsaber, just in case you didn't have enough time to catch it earlier on. I will print it once more. It's really a great gimmick. No, I was not. Okay, that's not working anymore. That's fine. All right, so just one slide about Endor Labs, really quick. We are a small startup, 3 years old, offering all kind of security services around software development. So we have a knapsack platform offering secret scanning, container scanning, first-party code scanning. But what we started with, and what is still kind of at the heart of our platform, is this program analysis technology, which where we actually have a lot of detailed code level information about the first-party code, as well as about all the dependencies that we pull into our application. So on the left-hand side, you see just a random application, right? First-party code, this is the stuff that you write. And then you have a bunch of direct dependencies that pull in transitive dependencies and so forth. This goes in the hundreds. You all know this, supposedly. And in normal or many kind of solutions, they kind of put labels, vulnerability labels, just on the boxes, just on the packages. And this results in a lot of findings generated for your applications. And what we do, using this code level information, we try to understand which of those packages and which of those functions inside those packages are really used in your application by your first-party code in order to reduce the vulnerabilities, the alerts to those that really matter in the context of your application. Real quick about me. So I'm a security researcher at Endor Labs. I started working on this whole topic of open source security around about 10 years ago. And my main interests are the detection, assessment, and mitigation of known open source vulnerabilities, right? That is exactly the topic I was mentioning on the previous slide. I'm the co-author of 2 open source projects. One is Eclipse Steady. So this has been given to the Eclipse Foundation at some point in time. It's this function level reachability solution just for Java. And the other one, Project KB, is a data set of fixed commits for vulnerabilities in open source solutions. So this is contains a couple of thousands of fixed commits for a couple of thousands of vulnerabilities, and that is useful input for researchers in order to develop these program analysis solutions. The second topic, and that is the topic of my talk, is looking into the classification and detection of supply chain attacks. Again, I'm the co-author of 2 open source projects here. One is Backstabber's Knife Collection. That is a data set that we have created in 2020 together with researchers from the University of Bonn in Germany. It's a collection of malicious packages that have been used in real-world attacks. Again, this is a data set helpful to develop detective controls. And the Risk Explorer, which is kind of a visual tool to explore all the possible attack vectors. I'm going to show a quick demo later on. So when we talk about software supply chains, we have to talk about open source. But just to make one thing clear, this is not in no means a criticism or critique of open source software, right? We all rely on it. I rely on it. Endor Labs, you all. So I just wanted to put this straight in the beginning. Good. This is the picture I've shown you and some other form earlier on. So on the top, you have your first party code, and then this layer, dozens, hundreds of open source dependencies. Here we have some statistics, how this looks like. So almost all of the software products include open source software. And those that include open source, the share of the overall code base is going up to 76, 80%, depending on the studies. Here, this is some statistics done, taken from a paper that I co-authored a couple of years back, showing different, characteristics of how those dependency graphs look like. So in those, across a couple of thousand Java projects at SAP, we had like 21% of those dependencies were direct dependencies, close to 79 were indirect dependencies. Here we distinguished the scope of those dependencies. 58% were compile time dependencies. So these were dependencies that your first party code required to be present in the class path in order to compile your application. And then we have 17% test scope dependencies, provided or system scope. So this different kind of scopes, this is existing in similar ways also in other ecosystems, right? NPM, for example, just distinguishes developer dependencies and then the other dependencies. What is important here, not all of them go into your production code. A test dependency, of course, is only present while you run your tests on your laptop or in your CI/CD system. So this is one way of an easy way to get rid of false positive alerts if you figure out this is just a test dependency. And here the last part is around how many of the dependencies of those applications were actually open source. Well, 86%, and just 14% were in-house dependencies developed by the same company. So these were a couple of numbers in terms of number of packages and the share of the packages. This is a different perspective. Here we count contributors, and I'm not sure whether you can read it really well. That is a screenshot taken from GitHub a couple of years back. They don't have this functionality any longer, but I find it very speaking as to how much you depend on all those upstream guys. So we don't count packages, we count contributors. This is the repository of Eclipse Steady, the thing I was mentioning earlier on. We had 9 colleagues, me included, working on the stuff, making commits on that repository. And there are 22,223 contributors to the upstream repository, which is just a crazy high number, which I find very speaking. I don't know why they removed this. I really like that feature, and luckily I took a screenshot. Another way to look at this is in terms of money. So here, this is some numbers published by the Harvard Business School in 2024. And they estimated the so-called supply side value of open source at 1.22 billion to 6.22 billion. Supply side value of open source means that if all the open source that is out there would be redeveloped, this is how much money we would need to spend. And the demand side value is estimated at 2.59 trillion to 13 trillion. Crazy numbers. Demand side value means if nobody would use open source at all, but everybody would just develop this functionality all in-house. Good. Now that you know, you knew already, but have some additional numbers maybe. Starting 2018, 17, 18, I would say, attackers started to kind of exploit and misuse this whole open source-based software development culture that we have built in the last 20 years or so, right? So they try to find ways to sneak malicious code in the packages that you pull at different times into your software development, be it on your developer laptop, be it in the CI/CD system. Supply chain attacks themselves, they're nothing new, right? So that term existed already before, but originally it was meant to kind of compromise the download servers or the vendor's infrastructure, so where people would download, a new version of some commercial solution. Right? The good prominent example is NotPetya. That was a supply chain attack in 2017, if I'm not mistaken. not paid. This was on a Ukrainian bookkeeping software. And so people downloaded an infected, malicious version of update of this bookkeeping software. And from the Ukraine, it basically spread across the whole globe. There were a lot of victims. One I still remember is, I think, a container ship logistics company from Denmark, Maersk. And I think it hit them to an extent that they were managing their fleet of container ships by paper. And then, as I said, in 2017, attackers started to also look more closely at open source software and ways to sneak in malicious code. What is important here, and the picture is maybe a little bit too overcomplicated for the message I want to pass. One important difference between supply chain attacks and the problem of known vulnerabilities in your open source dependencies. If you talk about these, vulnerable open source dependencies, what really matters is what goes into your production code, right? So imagine you have here an application A with a direct and indirect compile time dependency. This is what is running live, what goes into production. And so if you have a vulnerability, of course, you need to fix it. But if you have a vulnerability here, well, it doesn't matter much. It runs in your, test environment, for example. For supply chain attacks, all those scopes matter much more because, of course, an infected test dependency could also, do some damage, could exfiltrate your, secrets, GitHub tokens, AWS tokens, what have you. So that is an important difference between those two topics, let's say. Open source supply chain attacks. Here we have some screenshots showing just how many malicious packages are kind of published on registries like NPM or PyPI or Maven Central, even though most of those attacks happen on NPM and PyPI in the past. Other ecosystems are not as badly affected, at least not in terms of numbers. These numbers may be a little bit inflated. I don't really know how they count, right? Do they count packages or package versions? And I don't really know. What is without doubt is that there is a steep increase of supply chain attacks. And those range from very simple ones, mass-produced, automated ones, all those typo squatting attacks, to very targeted and very resource-intense attacks like this attack beginning of last year on XZutils, right? Where the people spent kind of 2 years to build up credible developer profiles up until they got granted the necessary write permissions on the repository and sneak in malicious code. Now I will walk you through a couple of examples, starting back in 2017 and illustrating different attack vectors. The first one here is from 2017. This was about gathering weak NPM credentials. So here, this was not an attack. This was a proof of concept, a white hat hacker, if you want, trying to understand the dimension of the problem here. So what he was able to do is he kind of got access to the credentials of more than 17,000 accounts in NPM. 16,900 of those accounts published something, right? And those 16,900 accounts that published something amounted up to 14% of the packages published at that time on NPM. If you only consider what they published themselves, if you also consider other NPM packages that depended on those, this guy would have had access and to influence more than half of the NPM system ecosystem at that time. Here are a couple of quotes of how, showing how kind of little awareness existed among the maintainers on good password practices. Great news here is that by now, two-factor authentication is required for maintainers of popular packages on NPM, on PyPI. There was a little bit of an argument going on from some maintainers, but I would say all in all that it was a very good development. And so this thing is not possible anymore like it was a couple of years back. This one here, I like, yeah, I kept this just because I'm speaking here in London. It was one of the earlier typo squatting attacks, and they took benefit from the fact that you write colorama or color a little bit different than our friends from the US. So the legit package was colorama with just with an O, and then the typo squatting attack was basically colorama with a U, like you spell it. What it does is it downloaded, so when you installed the tarball, it had a setup.py file, which is then executed. And what it did is it basically downloaded a Visual Basic script that contained then a clipboard hijacker in order to steal your cryptocurrency addresses. How do these work? They basically observe those malicious packages. They observe the clipboard. And if you copy something that looks like a crypto address, it would get it and exfiltrate it to the attacker. This one got persisted, and right, in order to make sure it's always running. The characteristic of this is like kind of a blueprint of the thousands and thousands of packages of that kind that you find on NPM. So you always have this. Again, you're not really able to read this so well, I suppose. But you had a large base64 encoded string, and so that in order to obfuscate it a little bit, make detection a little bit more difficult maybe, and and you would just decode this, execute it, download the stuff, and execute it. It's just like 10 lines of code, and that is how still I would say the majority of the malicious packages look like. Very often, you can see it just as a new way to deliver standard malicious stuff. So rather than only attaching this to emails, right? This is another distribution channel for the same thing. This one here hit the, let's say, IT news quite a bit. End of 2018, this was a successful attack on event stream. Pretty often used. So it had 1.5 million downloads per week, a lot of dependent packages. The thing here is that the attacker basically was granted write access or even ownership of this repository because the original developer of that package has lost interest in maintaining it. And so once he got access, he basically added a dependency to event stream, and that dependency, which was called flatmap, where is it? Flatmap stream, I think. Flatmap stream, there it is. That contained the malicious code. What was interesting about this one is that the malicious code did not trigger in the context of all downstream dependents, but it only triggered in the CI/CD systems of one downstream user, namely the Bitcoin wallet copay. And only in that case, it would alter the code of this Bitcoin wallet in a way that it monkey patched, it overrode the functionality of a function called credentials.keys, get keys. And well, the change was that once that thing is called, it exfiltrated again wallet credentials. And as so many times, we just discovered this, or the community just discovered this by luck, just because the malicious code contained one deprecated command, and somebody paying attention to those logs, passing by when building stuff, he noticed this and dug deeper until he eventually found it. Also very well known, maybe rings a bell for many of you, dependency confusion. That was found by Alex Birsan. And what he noticed is that thing here on the right. He basically looked at dependencies of applications, and he noticed that those dependencies here, they are not available on any public registries. And so he concluded, maybe these are internal dependencies. And then he had the idea of publishing packages with the exact same name on the public registry. And he could do this without any problem because it didn't exist, right? He could just deploy it. And then he was exploiting the fact that the dependency resolution process of package managers like NPM and PyPI, and I think there were also a couple of internal registries affected. When they are contacted or when they are asked to resolve a dependency, the vulnerability was that they preferred a public package with a higher version number over the internal packages. And so it was eventually just a vulnerability in the dependency resolution process of those package managers. That made quite some wave, and it still does. This is still a thing. Interestingly, this is mostly affecting bigger corporations, those that have internal packages, right? So the small startups that do not have all this infrastructure, they don't have internal registries. They kind of escaped this guy, Alex Birsan. Yeah, very nice finding. I think he earned a bunch of money with the bug bounties with this. A couple of years later, this is March 2021, an attempted attack on PHP. So this luckily didn't work out. There were 2 malicious commits noticed in the source code repository of PHP itself. And kind of commit message pretended to fix some typos. But in fact, what it did is it injected a backdoor that for a given HTTP header, it would extract a substring from the header and would run this command on the server running this infected PHP server. And that is a testimony of the kind of rigor and the quality of open source communities. This thing was just spotted a few hours later as part of routine post-commit code reviews. That is amazing. That is still, yeah, just great to see how open source communities react swiftly to those kind of incidents. If it had reached production, maybe you have thought PHP, what does he want? Well, you know, why PHP? Does it really matter? Well, it does. This is statistics from 2021. PHP is used by many websites. This is probably due to, you know, these typical content management systems. And this is still the case. So this is a screenshot of the same page, statistics from February 2025. So PHP is still a thing. So this would have had, yeah, far-fetched or far-lasting consequences. Problem here was the PHP guys, they operated their own Git server with some supposedly insecure configuration, which eventually led to this attack. By now, they have moved their code base to GitHub. Just a month later, I noticed right now there was another vulnerability in PHP Composer. So this was not an attack, but this could have led to an attack if it had been discovered by, yeah, a malicious guy. Composer is the package manager for PHP. This thing is also running on the registry, which is called packages.org. And that vulnerability would have allowed, you know, with plenty of download requests. And so that could have allowed an attacker to actually not only tamper with a single package, but to tamper with all the packages that are stored on packages.org. To the best of their knowledge, the vulnerability has not been exploited. Time did I actually? Yeah, good. Yeah, you don't know how many slides I still have. All right, but I like the examples. I think they make it very, you know, clear, and they are very illustrative of how attackers can, you know, sneak the code into the supply chain. This one is very interesting. It's about Unicode encodings. And so here, Unicode allows, they have something which they call BD, control characters. BD means bidirectional characters. This is to support languages that are written from left to right and from right to left. And what the guy here found is that you could use them in a way that what you would see in an editor or on GitHub when you review your pull request is different from what the compiler or the interpreter actually executes. So here you have something, a very simple kind of dummy example, where you have here kind of condition checking for the access level of the user. So you have here the condition followed by a comment, right? This is what you see or what you saw on GitHub. Now, but what is actually kind of existing, and here you see in red and blue the BD control characters, the actual condition is looking different. And so this sounds, and so this is what the interpreter would actually execute. And so this is a little bit of a toy example, but it is imaginable to conduct an attack, right? Following up, GitHub added this small exclamation mark. Maybe you have, if you see it. So this is just to say, here are some special Unicode characters in your code. So maybe, look more closely. This also affected Visual Studio Code and a couple of other IDEs. I think I should hurry up a little bit. No, this is also interesting. NPM. This was a vulnerability again. The root cause of this problem were inconsistent authorization checks. So if you uploaded a package to NPM, if you wanted to publish something, the vulnerability was actually that the access control checks were done against the package as identified in the URL. But the actual package name was also consisting in the payload of your post request. And so you were checked against one package, but what you have deployed was something completely different. Again, to the best of their knowledge, it has not been exploited, but the logs only lasted until September 2020. Now we are getting closer to today. But I think I will skip this. I will rather go a little bit more in detail on what you have heard a couple of weeks back, which is TJ Actions. And that is actually, so it hit made quite some waves also. So here there was some malicious code added to a JavaScript file of this GitHub action, right? And so if you happened to use this GitHub action directly or indirectly, this script or this piece of code would actually dump the memory of the runner, which is containing the secrets of your repository, and it would print it to the log. Interestingly, it only printed it. It didn't exfiltrate it. Would have been much easier for the guy to collect the stuff. I don't know why they did it like this. Maybe to stay under the radar in order to prevent kind of more suspicious network calls. How did they get into this? Well, the commit that introduced this malicious code was actually impersonating Renovate bot. And this is really, impersonating GitHub commits or Git commits is quite easy. It's just a matter of changing a configuration setting. You put the email address of the guy that you want to impersonate, and then in the GitHub UI on the web, it looks as if it has been done by that guy. The attacker added this commit to a fork of the legitimate Renovate bot, and the repository was configured in such a way that in a pull request of the legitimate Renovate bot, and the repository was configured to merge those pull requests automatically. This is how kind of sneaked it in. And then you also changed the tags of the TJ actions to point to this malicious commit, right? And I will come to this in a second. First, he only changed the tag of one version, namely one that was used by Coinbase AgentKit, yet another crypto technology. And then later on, he changed all the tags of TJ actions. The impact of all that was that the workflow secrets of all direct and indirect users of changed files, there were 23,000 or so, get locked if they executed the workflow during the time of that compromise. And I will have some numbers on this later. Now, how did he get write access to TJ actions, right? I was just explaining what happened at TJ actions. In order to get there, there was a sequence of attacks on other upstream repository, and all those upstream repositories, let's say, were involved or were kind of compromised through pull requests, In the same way, changing tags, exfiltrating personal access tokens that eventually gave him a personal access token of a maintainer of TJ actions in order to do the things I was mentioning in the first bullet point, or the first couple of bullet points. I really recommend reading through the write-up of this Palo Alto Network Unit 42. You have the link here. They did a great job in figuring this all out. There are a lot of takeaways for this one here, from signing commits, protecting your branches, to pinning your actions to commits. This is which was, I think, a huge or maybe is still a misunderstanding of many GitHub action users, that if you just refer to a tag when you use a certain GitHub action, you actually pin something that is mutable, that can be changed. So, right, you maybe think version 1 of that and that action is always the same thing. It is only the same thing as long as the tag stays the same. If an attacker changes the tag, your version 1 is just using something completely different. That is why you should pin your actions to the commit hashes and not to version tags. GitHub has something in the making to overcome this deficiency. I hope they are going to release this soon. And then other kind of, avoid personal access tokens if there's no way around, restrict their permissions and the lifetime. Also avoid the pull request target trigger. So this is one trigger that starts a workflow, and that was at the root of all this chain of compromised repositories, because the thing is that those are workflows that can be started also from forks, and as part of those workflows, you have access to the secrets of the repository that you forked, which is a huge problem, obviously. So those have to be used with a lot of care. And I'm not going into the last point. Right, so TJ actions, I think the lessons learned, well, the takeaways I showed earlier on. But again, I must say, I think we got lucky. Okay, sorry. I'm used to waving my hands around, so that is not working well with me, Mike. So yeah, we got lucky. 23,000 downstream repositories depended in some way or directly or indirectly on TJ actions, but only a smaller number got compromised, really, because the attack was discovered relatively quickly. So this is from a blog post I wrote a few days after the attack. I tried to understand, well, how many leaks got actually leaked? How bad was it? Was it really 23,000 repository? No, it weren't. So I found 5,400 something repositories that directly used it. So I just used the GitHub search in order to figure out which workflow files had TJ actions. So this number is a bit smaller, but because it doesn't consider indirect dependencies, right? Then I looked how many of those repositories actually ran a workflow in the 24-hour time frame. Not so many, 640. And then how many secrets were actually leaked? Again, not so many, 218. Most of them were these GitHub tokens. Again, you can read this. Those are short-lived. They live only as long as the workflow runs, or at most 24 hours or so. And then there were a couple of AWS tokens. And other things. I notified, of course, the repository so they could delete their logs. So actual impact, not so much, but only it was so quickly discovered. I think it could have been much, much worse. Now, you have heard a lot of examples all across the place, very difficult to follow maybe. And so I would like to use a few slides in order to, bring some system into it, some order in it. And so again, as a quick reminder, you all know this. This is how the code flows from a versioning control system with contributors and maintainers to some build system where all the upstream dependencies are pulled during the build and the final artifact is published in the registries. And then the consumers, we can either build the stuff from the versioning control system, which virtually nobody does, or we just download the prepackaged stuff from registries like PyPI and NPM. Now, this is kind of showing all the different spots where the attackers you know, that the attackers considered, that they looked at in order to conduct their attack, or could have done if they were able, for example, to find vulnerabilities first. So just a few examples here. This Trojan source, right? The BD control character stuff. There was a problem with versioning control system and management platforms like GitHub in order to show those properly. And then we have here contributing as a maintainer, right? If you compromise a maintainer in one way or the other, you can actually change across the board, right? You can you know, tamper with the artifacts of the project and the distribution system. You can configure the build system or change it whatsoever. Or, for example, you create a name confusion where consumers then are confused in the name of the alleged package and may download a wrong thing. So this is making this a little bit more structured. And what we did then is basically to create a taxonomy. And this is basically, we have looked, and if I say we, this is research done by Pier Giorgio Ladisa and myself and a couple of other guys from the University of Rennes, where we basically reviewed hundreds and hundreds of, you know, white papers, attacks, all the stuff similar to what I've shown before, in order to build this taxonomy. Again, you cannot read anything of this. The idea is, this is it takes the form of an attack tree. At the top, the root node of the attack tree is the goal of the attacker to conduct a supply chain attack. And as you go down in the attack tree, you basically refine this goal to smaller goals that allow you reaching the top level goal, right? And the use cases of this is, of course, to raise and create awareness, to support threat modeling activities, but you could also use it to scope penetration tests. And so there was an interactive visualization of this thing, originally developed back then at SAP Security Research and forked at Endor Labs, and that is what I'm going to show you now. If I manage to change this. So this is this risk explorer hosted here at Endor Labs, and you can now basically read this. You can explore this attack tree, right? So here's the top level goal. Then we have three sub goals. One is this create name confusion, and wherever you click, you basically open the sub nodes, and every node here comes with a description, a couple of references. References could be white papers, could be attacks, could be research papers, academic papers, and then on the right-hand side, you have a couple of safeguards, right? So this makes this whole thing a little bit more structured. It helps you understanding the problem space, right, and go to the respective resources, right? So here we, for example, we have this typo squatting. So this is the second branch here. It's all about naming confusion. Typo squatting is just one. Combo squatting, branch checking are just other similar techniques. Branch checking, for example, if you see a package that starts with AWS dash, you might think it's coming from Amazon. And so you may think and trust it more if it didn't start that way. And then here in the lower branch, you have basically the biggest number of attacks. Here we find the dependency confusion. We find techniques compromising CI/CD systems such as cache poisoning and so forth. All right, now we go back to the presentation. Good. Now, how do we detect this? Well, there are three techniques that I would like to briefly touch upon. One is we look at metadata, and by metadata, I mean package name, I mean the account that published the package, how long does this account exist, what were his past contributions, which other packages were published with this account, you know, what are the publication times, do the publication times on a package of NPM correspond to the typical daytime publication packages, or maybe they're suddenly done in a time zone at a time that is uncommon. Well, this is evaded by attackers through the creation of credible accounts and creating a package history, maybe creating a package that has alleged reason, alleged raison d'etre, and then only at a later point in time to add malicious code. The other one is static methods in order to detect malicious code. So here you would again use program analysis techniques, maybe look at API calls, you maybe build a call graph, these kind of things. You search for obfuscated strings, high entropy strings, these things. And they are basically can be evaded, for example, by splitting the payloads. I have a nice example later on, dynamic calls. So the attacker just puts everything in a big eval and as such escapes static analysis. And the last here is a dynamic, so kind of detection, where you run the stuff and then you try to see whether it does anything malicious. These are kind of these behavioral approaches to malware detection. Again, nothing new. A great project in this context is the OpenSSF project package analysis. They go great lengths in order to trigger as much code as possible of a package uploaded to PyPI, for example, so they observe any behavior. Unfortunately, this can be relatively easily avoided by just delaying or conditioning your execution, right? If you just wait 5 minutes before you execute malicious code, nobody running these sandboxes can pay the money in order to do this for thousands and thousands of packages. Right, this is a nice example for, well, nice, I keep on saying nice. It's all of that is not nice, obviously. It's, let's say, interesting. So if I say nice, I mean interesting. This is an interesting example of malicious packages that I found. This was in 2023. And this, what made it interesting is that the malicious payload was split across different packages. So in order for the malicious functionality to work, both of those packages had to be present in the dependency graph of a victim project. It was downloaded a couple of times until we told PyPI to remove it, which they did very promptly as always. So the one package was called Easy. It was basically an SQL query in order to find cookies in the SQLite database of Chrome. And if they found cookies, it would exfiltrate them in order to impersonate the Instagram user to whom this cookie belongs. And the other package, well, actually, the exfiltration was done in this other package, TTLO, which called a functionality of the previous one in order to obtain the cookies. And so that was interesting. Again, both of them had to be present. Still, I didn't manage to figure out how the attacker made sure that both of the packages are present in the victim package, because one didn't depend on the other. So that is a little bit unclear. I'm not sure, maybe they were just still in the making. If you look at these malicious packages, you see they publish a couple of kind of development versions until they reach a version that really does any harm and that works properly. You will be surprised how many easy development mistakes and bugs are contained in these packages as well. So here, this evasion technique was the split. And so what was interesting is the split was between packages, but also it used functions from different files. And so many of the more simple code scanners, they are limited in kind of the context that they look at. So they can only look at a given functions code, or maybe the code of an entire file. But by splitting the payload across multiple files, it's more difficult. So you would need, in this case, interprocedural data flow analysis. You would need to understand how does the data flow between functions of different files within the package to understand what's going on. To understand that a base 64 encoded string from one file is flowing into the decode function in another file. And then again here, this is what I mentioned, separate packages. So here you need whole program analysis in order to find the complete malicious behavior. you would need to analyze all packages together, which is again beyond the scope of many scanners. Two or three slides to go. Selected safeguards. I mean, the space is so big. There are so many attack vectors, as you have seen with the examples and the systematization. I cannot really talk about all. So I just picked a few that I thought are noteworthy. But this is really a very subjective selection. Some of them are relatively cheap. Others are $3. So one is, let's start here. Remove bloated dependencies. I think this is where we have the biggest potential, because we pull in all those packages, but we do not use all of them. Some of them are just lingering around. They get installed, but we do not touch a single function. Let's try to remove those. A bit more complicated are those cases where maybe we use a subset of the functionality. Here you could imagine we basically rewrite the open source package to only contain what is really reused. This is exactly how it is done in Go, where you build your Go binary. Great. But that is, I think, the only example I can come up with quickly. In NPM and Java and PyPI, you always pull everything. You always install everything. So this whole topic, there's a lot of, let's say, potential for improving our supply chains, just reducing it to the code that you really need and not try to install and, pull everything. One thing that is this is more on the $3 side of this examples is build dependencies from sources. So you don't pull anything any longer from PyPI. You just clone the repository, build it yourself, store it in some internal registry. Obviously very expensive. This is how Google does it. And maybe bigger players predominantly, I would say. Very expensive, but very effective because it cuts off. You remember one of the previous pictures, all the attack vectors looking at the build systems and all at the registry on the right-hand side, you get rid of them in one shot. Again, expensive. Digest and version pinning. And I think this is something that I always hesitate because I talk both about known vulnerabilities in your open source dependencies. And so if you don't pin your dependency, there are chances that you automatically get the fixed, secure new version of that package is great. So that in that sense, if I take this head on, I would say don't pin in order to benefit from that. But of course, if you do this, you also automatically consume any malicious version, right? And so, and if I have this head on, I would maybe say pin it rather than not. My approach is I pin, but then I have some automation in place to remind me of there are some vulnerabilities and help me bumping the version. But this is also very ecosystem specific. So there was recently a research paper that I didn't put in the references here. Maybe I can do this before I share the slides. There was a study on NPM dependencies and the question, pinning or not, what is better? And it turned out that if you pin your direct dependencies, you ended up with more versions of your packages than if you didn't pin it, which is because you kind of constrained the version resolution in such a way that it copied multiple versions of the end package in your node modules folder. So it's very peculiar. You need to look at this from ecosystem context to context. And then again, we talked about GitHub Actions earlier on. Here you should pin it to the hash, please. Two other kind of safeguards here. One is to isolate build jobs and build steps. Isolating build jobs basically means you run every build on a clean slate. You do not share any resources across different builds because that gives room to cache poisoning attacks. You have your one build, and this guy maybe changes your local M2 folder where you have all your cached Java artifacts, and those will be used by the next build of the same project or a build of another project running on the same machine. But this is even true, in my mind, for build steps. So if you again think Maven projects, you have different steps from compiling to testing to integration tests to packaging to deploying. And the thing is that in your typical POM file, you have plenty of plugins doing all sorts of things, generating code, generating documentation, running the test, and so forth. And the thing is, all those plugins have the same permissions on the artifacts produced during the build. So your test plugin has write access to the classes that have been compiled earlier on. They can tamper with the bytecode, which should not be the case. But I don't know of any kind of ecosystem isolating build steps. But I think this would be something to look into it. And for the same reason, what I just said, you should minimize your release jobs. So those build jobs that produce the artifact that you will use in production, that you publish somewhere, they should run with the smallest amount possible of plugins or extensions. So good. Second to last slide. Not sure how I'm on time, really. As always, I didn't pay much attention and just talked. So, perfect. Name confusion attacks, well, live with those attacks. They will never go away. They exist in any platform, in any marketplace that people look at and people download stuff from. It's just too easy to conduct. It doesn't cost the attackers much to copy malicious code, give it another name, upload, live with it, and get used to it like you got used to spam, right? The other thing is, what I think, if I may make a prediction, what we see going forward is more a compromise of legitimate packages. So where people try to socially engineer themselves into the source code, into the repository, and inject malicious code into the sources. One technique that could be useful in this context is this kind of impersonation of users, like this Dependabot impersonation you have seen. In TJ Actions, they impersonated Renovate, another bot, and people just looking at the names may think they come from this legit bots. And sometimes they don't, right? And what I'm personally most afraid of are these deliberate vulnerabilities, right? So what I mean by deliberate vulnerabilities is code that if you see it, doesn't, let me start differently. For all these typo squatting attacks, if you see some base64 encoded string and a setup.py, well, you know there's something fishy going on. A deliberate vulnerability is something that is not obvious. This is maybe a missing authorization check or a wrong authorization check, or maybe a regular expression that is off. Good luck recognizing such regular expressions. And an example for this is the attack from 2003 on Linux. This was a malicious commit, and what made it malicious was actually a one-character difference. So here, what happens at the end of this condition, here we don't check whether the current user is root, because if we wanted to check, we would have two equal signs, but we actually make the current user root. And so this would be a good example of a deliberate vulnerability. Back in 2003, it didn't make it in the kernel, luckily. That's it. Again, for the... Yeah. That's the lightsaber, and if you do not only want to have one, but also be able to use one, you can also scan this other QR code, because what we did is we basically offer a stunt training session with a Hollywood stunt trainer, so you can properly use it. So for that, scan, and we will reach out once this is going to happen in London.
We have lots of questions online about this stuff. One question online, questions from the audience. Question online was, any updates on when Dependabot will support scanning actions that are referenced by commit actions? Updating all this manually is a pain.
No, I don't have any insights into what GitHub Security is planning to do with Dependabot. No, I'm afraid. But I must say, The pain of doing this. Oh no. No, I completely agree. That is a painful exercise, maintaining this and doing this yourself. I also have to do it. I hate it a lot. Maybe the good news is it's actually easy to detect, because unlike problems in source code, the structure of those YAML files, which you use for defining your actions, make it very easily accessible to code scanners. But again, I don't have a good solution to automate this, I'm afraid.
Questions from the audience? Yeah.
Should not be too difficult.
My question is about dependency, fusion and interfusion and GitHub actions. This with the source. What do you think is applicable main interfusion for GitHub actions? For example, you have private GitHub deployment, you have reusable GitHub action, private deployment, and somebody malicious creates public GitHub action with the same name, and in this way you can compromise your pipeline. But what do you think is applicable?
Yeah, that's a very good question. I think you just give me an idea what to try out. Now I don't have a good answer myself right now, but I think it's a worthwhile direction to investigate. Thank you.
No more questions? Okay, then let's thank Henrik, and we're going to go to 10-minute break.